So far, our description of phase change has been mostly qualitative, understanding what kind of interactions break when we melt and boil, understanding the ranking of intermolecular forces, etc. Now let's try to understand it in a more quantitative point of view, and you may need a little bit of units of factor conversion to understand that, and reviewing what we have seen in the past when it comes to internal energy. Let me remind you that there are some exothermic reactions. An exothermic reaction is a reaction which the products have a lower internal energy than the reactants, and that means the energy will be as heat being kicked out of the system, and the change in enthalpy therefore will be negative. You can think of phase change as a chemical reaction, even though they still keep their identity through solid, liquid, and gas, unlike this reaction of combustion. So methane disappears and becomes CO2, but still, phase change can be understood as a chemical reaction because it involves some energy and there's some breaking of, in this case, intermolecular forces. So from liquid to gas, that's a vaporization process. Because the gas has a higher internal energy, it means that this is more positive, the final is more positive than the initial, or it's higher. Therefore, this is delta H is positive, and this is an endothermic process. So you need to provide some heat. No wonder, right? When going from liquid to gas, to vaporize your liquid. And the opposite for when going from liquid to solid. You need to remove some heat because internal energy of solid is smaller than the internal energy of liquid. So your delta H will be negative. Okay? So this means that when having a phase change, you will have an enthalpy associated to that specific change. For example, the vaporization is the enthalpy needed to typically 1 mole, or to vaporize 1 mole of that specific substance. And the heat, and we said that vaporization is positive because you need to provide heat, it's endothermic. It'll be the same magnitude as condensation, but changing the sign. Okay, so, and that's important. The same energy that it takes to go from solid to liquid and from liquid to vapor is the same energy that you need to remove when going from vapor to liquid and liquid to solid. Okay, so a little bit more. We can talk about internal energy, and remember that this is H is enthalpy, but any substance at any given temperature has some enthalpy. Okay, so when you take ice at, say, -25 Celsius all the way to water vapor at 125, you go from a lower internal energy to a higher internal energy. Okay, and so it does not need to be only one single phase change at a time. It may be a big jump. And one property of enthalpy and internal energy, what we call it, is it's a state function. It means it does not depend on the path. You just need to do the increment of final minus initial. In other words, this means, what this is trying to say here is that the energy that it takes to go from ice in one single process all the way to vapor at 125, in other words, H3 minus H1, so to go from solid to vapor in one single process, is the same that if we did the process in 2 steps. If we decided to go from ice at -25 to water at 50 Celsius, and then from water at 50 Celsius to vapor at 125. So it'll be the same as going from final water at 50 Celsius minus ice at 25 plus, so here you have your 2-step process. Okay, so in here we went from solid to liquid, and here from liquid to gas. This is what a state function is. You can use enthalpy as a variable at a specific temperature. Okay, and these two quantities should be the same. In other words, the quantity for going from solid to vapor in one single step from liquid to vapor. Let's be consistent. These two processes should have the same energy. Okay, so what you see here is a cooling curve. That tells you the energy involved in going from gas to liquid and from liquid to solid. Few things that you may want to see is that, of course, the temperature needs to decrease as you go from gas to solid, and few things. At the phase change, the temperature is constant, and that's a very important distinction. During phase change, the temperature is constant, and so which is not the same when you are heating up or cooling off your liquid, gas, or solid. Notice that if you remember what we call the MCAT equation, right? The heat is equal to mass to the heat specific heat capacity and the change in temperature. You can only apply this in pure phases, never when you have a phase change. Okay, so you can only apply this equation when you have either pure liquid, that is during this process, during this phase, or you can apply this when it's gas, or you can only apply it when it's solid. Okay, you will not apply this equation during phase change. Okay, for that we will need to use just the enthalpy of vaporization or enthalpy of fusion. Okay, so other observations. Notice that the enthalpy of vaporization, in other words the heat that it takes to vaporize a substance, is usually larger than the enthalpy of fusion. How do you know this? Well, this is the heat that it takes, the heat that you need to remove when going from gas to liquid, which is much larger than the heat that it takes to go from liquid to gas. Why is that? Well, vaporization takes a lot of energy because you actually need to detach the molecules from all of the molecules around them. So the process from liquid to gas, you need to break more bonds when going from liquid to gas than if you go from solid to liquid. That should be something that should be somewhat intuitive. At the same time, and I will repeat it again, you can only apply this equation only when you have pure gas, pure solid, or pure liquid. Notice that the heat capacity of gas, liquid, and solid will be different. So you cannot apply the heat capacity for water liquid if you are warming up, say, ice. Okay, so we'll have to run an experiment for that. So let's see if we can figure it out. First, let's try to understand what is the relationship between heat and mass. In this case, it's asking for how much mass of water in grams can be vaporized at its boiling point with this much heat. Okay, well, what does this tell us? This tells us that for 1 mole of water, you need to provide this to vaporize it. Okay, so it's asking for how much mass. I have this much heat, these many kilojoules of energy that I want to use to vaporize water. Okay, what does the factor conversion tell me? It tells me that I would need to invest this much energy, and notice that if it's vaporization, this should be positive, for 1 mole of water. Okay, and I know that 1 mole of water is 18 grams. Okay, this will give me the grams of water that I can vaporize with this much energy. The next problem in a separate video will be about combining heat capacities and enthalpies of phase change all together. So it's going to be long, so we're going to do it in a separate video.